I love singing, and I really like Skyfall by Adele. So hey, maybe I could try singing it. Let the sky fall when it crumbles. We will stand tall and face it all. That didn't sound so good, but hey, I'm a programmer, so I can fix it using code, right? Let's see if I can autotune my voice with Python. Hi everyone, this is Jan Wilczek from WolfSound.com, and if you're new to this channel, here you can learn how to process sound using self-written software. And what can be better than processing your own voice recordings to make them sound in tune? Singing in tune is very difficult, so let's see what do we need to do to achieve it with code. First, we would have to find out what the pitch actually is at a given point in time. We call this problem in digital signal processing pitch tracking, pitch estimation, or pitch detection. Second, we would need to choose our pitch adjustment strategy, so how we would map the actual pitch to the desired pitch. Should we use a musical score? Various options are available here. Third and final, we should adjust the pitch of the recording according to the calculated desired pitch. This step is called pitch shifting. The whole procedure is called pitch correction in the digital audio effects community, but more broadly it is known as the autotune or the Cher effect. So how to implement it? We'll use Python because it's the fastest approach when it comes to implementing most DSP algorithms. The first step is to Google around for a pitch estimation algorithm. After a few minutes, we arrive at the conclusion that the state of the art is the PYIN algorithm. Now, I won't go into details, but PYIN is a probabilistic version of the YIN algorithm. The YIN algorithm estimates the pitch from the time domain signal. PYIN assumes that there may be multiple estimated pitches, at each with some probability. It then estimates the most probable pitch trajectory over time using hidden Markov models. If you are interested in the details of these algorithms, you'll find the links to the original papers in the article on WolfSound.com, which I have linked to in the description below. Now, how to perform pitch shifting? There are various approaches to this problem, but we'll use one of the most popular ones, which is called PSOLA, which stands for Pitch Synchronous Overlap and Add. Without going into much detail, let's just say that this algorithm disassembles and reassembles the signal in the time domain to fulfill its task. You don't need to understand PYIN or PSOLA to use them. The best thing about these algorithms is that they are readily available in Python packages. Finally, we need to decide on our auto-tuning strategy. There are various approaches here. We could round to the nearest note, we could use sheet music, etc. But since we know that Skyfall is in C minor, we can use that knowledge and round the estimated pitch to the nearest pitch from the C minor scale. How this can be done will be clear when we code this together, so let's dive right into it. Alright, so we're here inside Visual Studio Code, and as you can see I have the vocals file right here. It is the shortened one, so it's faster to process. And now we can go and we can actually start the processing. So first thing that we need to do is we need to load our file. So what we'll do is we'll write y and something great, and we'll do lib rosa load, and we'll do Skyfall vocals.wave. And what we want to have is we don't want to resample this, and we also don't want to convert it to mono. And of course for this we need to import librosa. Okay, and the next thing that we need is that for simplicity we'll simply process one channel of audio, so we'll simply take the first channel. So if there's more than one channel, then we'll simply reassign y to take just the first channel. So that's how librosa load works. And okay, now what we need to do is we actually need to call our autotune. So we'll write pitch corrected Y and we'll say autotune sampling rate. And actually that's everything that we need here, apart of course from the Y argument. All right, and then we'll simply create an output file path. So we'll have something like this, and maybe it will be easier if we have this as a path object. So we may again have something like this. Pathlib is a very nice utility, and we'll write something like this. Parent, right? And we'll have it here, file path stem plus pitch corrected, and we'll also add the suffix. And now we can use the sound file to simply say, okay, under this file path, write our pitch corrected Y with the sampling rate. So what we're doing here is we're taking this name, Skyfall vocals, we're adding to it pitch corrected, and we actually, that's maybe too much. Okay, pitch corrected, and then the extension of this file name, and then we write it with the sound file library. So let me import this. Okay, so this was our input and output, and now let's go to the autotune. Okay, and here we need to do three things, right? So we need to track pitch, we need to calculate desired pitch, right? And then we need to correct the pitch. So we need to actually do the pitch shifting. All right, so to track the pitch, what we'll use, as we said, we'll use librosa PYIN. And it has the signature, so we give it Y, the signal, and then we pass in frame length, and we'll set it to like a larger parameter, which will be 2048. So this is the length of the analysis frame. And then we'll have hop length, again, is a predefined parameter. And I'll take a very typical value, which is just the frame length divided by 4. Okay. And now the sampling rate, and also the minimum frequency and the maximum frequency. So this of course may be fine-tuned, so let's take something easy. So we'll say librosa note 2 Hz, and we'll say C2, and here we have F max, we have, sorry, this was supposed to be C7. So from C2 to C7 we'll be able to determine the pitch. All right, and now what it returns the F0, and then it returns the voice flag, and it also returns the probabilities. So what we'll use here is that we'll assume that this F0 has nans wherever there is no audible pitch. So there's like the sound is more noise-like. So actually that's all that we needed to do here. So now what you need to do is we need to correct the pitch, and we'll do it like this. Let's call it correct pitch. So you will have correct pitch, and just for a second I won't write anything here, because what I would like to do here is like to already do the pitch shifting. So I'll do PSOLA vocode and pass it the input signal, and then we need to pass it the sampling rate and then the target pitch. I will say simply corrected F0 and then minimum and maximum frequency. Okay, perfect. And for this, of course, I need to import PSOLA. And now we can do the last thing that's remaining. So we need to correct the pitch. And for this, we'll use the strategy to round to the nearest pitch that is in the C minor scale. So what we'll do is we'll first allocate the memory. So we'll say something like corrected F0 NP0 like, and NP is just a shorthand for NumPy, right? And now for each pitch, corrected F0 of I will say correct. Okay, and we'll have a function that simply corrects a single scalar. It will be easier to write. So if NumPy is nan of 0, then return the nan value. And then what we need to have is we need to get the degrees of the C minor scale. So we'll do we need to have it something like librosa key to degrees, and here we need to pass in C minor, and now we need to append the first degree repeated, so one scale above, and I'll shortly explain why we need to do this. So do something like this, plus 12, because that's how many semitones in an octave there are, and this is because key to degrees will return the degrees of a scale, but it won't repeat, you know, the first element, the first degree as the last one. And if you think about it, if we are very close to 1 octave higher from the first degree, then we likely would go to the first degree again. But in the rounding procedure that we'll see, we would round then to the 1 degree lower. So we need to add this last degree to be able to round up from like the high pitches in this, or like pitches which are closest to the highest degree. That's the goal. So okay, now what we need to do is we need the MIDI note number, MIDI note, and this will be Librosa Hertz to MIDI, and we'll pass in F0 here. And then what we need to do is we need to calculate the degree of this MIDI note, and this again will simply MIDI note modulo 12, so the number of semitones in an octave. And then we need to find the closest degree to this one. So let's write it like closest degree ID. And this will be NumPy argmin, and we'll simply have it difference between the degrees and the degree. So what happens here is we take the degrees from the C minor scale. I can even maybe write it like this so it's clearer. So we'll calculate the differences between this degree and the C minor degrees, And where this difference is smallest, then it means that this is the closest pitch. And here you can see that's also why we appended again the first pitch raised by an octave. Okay, so we already know which pitch we want to go to. So now what we need to do is we need to calculate the difference from this degree to this closest degree. So we'll say something like degree difference. And we'll have this C minor degrees and closest degree ID. And why we need this? Because now we need to subtract this from the MIDI note to correct it, and we can return the value in hertz. So what happens here is we are in the degree range, right? So from 0 to 12, and we simply include the distance in degrees from the current note to the desired note, let's set the closest one to the C minor scale, and then we correct the MIDI note, but we need to correct it in the proper octave. So we cannot correct it in the degrees, we need to correct it in the proper octave. That's why we subtract this difference from the MIDI note and not from the degree. And then we return this MIDI note converted to hertz. All right, and when we've done all this, then we can do something like this, because we may end up with a like jerky pitch function, and we don't want to do that, so we will need to smooth it out. And for this we can apply a so-called median filter. So we'll have here corrected F0, and we'll pass in kernel size 11. And what it does, it will calculate the median of each 11 values and replace the value with this median. So it's basically a form of smoothing over time. And for this we of course need import SciPy signal as sig. Okay, and the last thing is we want to preserve the nans. So what we need to do, because the smoothing can actually remove the nans, so we need to do something like this: smoothed corrected F0 of so what we're doing here is that wherever there is nan in this smooth pitch trajectory, we assign the original pitch value. So we can even go further here. We could actually maybe assign the corrected F0 value. Okay, and now I can. And now we return this pitch, and that's all actually. So we can already run this function and see if we get any errors. Hop length is not defined. Okay, it's a typo here. Float object cannot be interpreted as integer. Okay, do I need to pass in the names here? Is that the thing? Okay, because I need to, I know. So this needs to be integer division, all right. Because hop length needs to be an integer, not a float, because division by 4 would simply produce a float, but we need to divide with this double dash so that it stays an integer. Okay. concatenate. Great, so it actually did work, and as you can see we have our pitch corrected and pitch vocals. So we'll listen to it shortly. This is the original one.
Werewolves collide and days are dark.
And this is the corrected one.
Werewolves collide and days are dark.
Alright, that was actually pitch shifted and pitch corrected. So now let's listen to the full example. Alright, it is time to listen to the original recording and the Python autotuned file. To make it easy to compare the two tracks, I am using the TrackSwitch.js library from Audiolabs in Erlangen. The sky falls when it crumbles. We will stand tall and face it all together at the Skyfall. Not bad, is it? There is still room for improvement. We could introduce the amount of correction as a parameter, or further process the vocals with more effects, but for now that's enough. It's time for you to auto-tune your voice. And a big shout out to the backing track of Skyfall, which I have found on YouTube. You can find it in the description below. In summary, in this tutorial we created a simple Python utility that allows us to auto-tune our vocal recordings. The algorithm uses the PYIN algorithm for pitch tracking, the PSOLA algorithm for pitch shifting, and rounds the pitch to the nearest clean pitch from the given scale. We then use the program to auto-tune my poor vocal recording of Adele's Skyfall. The quality of the results are for you to judge. I have linked to the full source code of this tiny Python program in the description below. There you'll also find the link to the full article on WolfSound.com. And if you're interested in how to become an audio programmer and work on similar topics on a day-to-day basis, I have a resource just for you, my audio developer checklist, which you can get at WolfSound.com/checklist. There I listed all the knowledge that you need to become an audio developer. If you liked the video, don't forget to like, subscribe and turn on notifications. Thanks for watching and see you in the next one. Take care. We all stand tall and face it all together at Skyfall. Let the sky fall. We will stand tall at Skyfall.